Okay, so today we are gonna introduce the fasten and screw components. And what's the purpose for screw and the fastener? So why we need the fastener or screw like the nut and screw? So if this machine is gonna be assembled, and after assemble, it's be designed as easily disassembled. And if this component is non-permanent fastened or non-permanent assembled, that means this machine or this component is easy to maintain, right? If some part of it is fail or is broken, and we can just replace it, okay? Just disassemble it. And also, if this machine is required to be adjusted, okay, for the long-term use. So the reason for the screw and the fastener is for the permanent fastener. Okay. Okay, so there's some the geometric define of the standard of the threads. Okay. So first is the pitch. So what is pitch? Okay, pitch is the distance between adjacent thread, reciprocal of threads per inch. Okay, so the distance between adjacent thread, right? So you can from the crest to crest, or you can from the roots to the roots. Okay, and the major diameter is the largest diameter of the thread. Okay, the larger diameter of the thread. Okay, so it's called the major diameter here. Okay, and the minor diameter is the smallest diameter of the thread. Okay, that means we can define it from the roots to the roots, right? So this distance is defined as the roots, the minor diameter. Okay, and the pitch diameter is a theoretical diameter between the major and the minor diameter where the tooth and the gap are same width. What's that mean? What's that mean? Okay, so the pitch diameter is it's not a real diameter, so we can define it as when the tooth and the gap are the same width. That's mean we have the width of the tooth right here, which is equal to the gap diameter here. Okay, so when these two diameter are the same, we can define the distance between where the gap and the tooth at the same width is the pitch diameter right here. Okay. Okay. So we can define the distance, right? When this gap diameter, the gap width is equal to the tooth width, right? So we can define the diameter is the pitch diameter. Okay, for the standardization of the threads, so for the American National thread standard, define a basic thread geometry for the uniformity and the interchangeability. So for these American national threads, which will be simple as the UN, which is the normal thread in the English units, or the UNR, represent the greater root radius for fatigue application, also in the English units. And for the metric thread, right, it's been using in SI units, right? The M series for the normal thread and MJ defines the greater root radius, okay, greater root radius. Okay. Okay, so if the thread with the multiple screw, okay, okay, thread with the multiple screw. So for the single, double, and triple thread screws, it can be defined as when the lead equals to 1 pitch. We can say it's the single thread screw. Okay, so when the lead equals to 3 times pitch, it is defined as the triple thread screw. So that's mean when this screw is a single thread screw. That's mean when the knots rotate one terms. That's mean the lead equals to the pitch. Okay, and for this double thread, okay, for this double thread, that means the lead when this knot rotates one turn. Okay, and this one turn, one lead equals to 2 pitch. Okay, 2 pitch, and so on, and so on. Okay, so you can have the single, double, triple, or the quadruple thread, and so on. That's mean the knots, the distance of the knot movement depends on the multiple thread screw. Okay. Okay, so here's defined geometry. So you can just look at it. So I think it's not quite difficult to understand, right? Okay. So we have this major diameter here from the largest diameter, right? And with the pitch diameter, dp, that's mean the gap width equals to the tooth width, right? And the roots diameter, okay? Or we can call it the minor diameter, a minor diameter, okay? Okay, so also we can define the threads as whether it is coarse or fine. So for the thread height of the coarse bolt is greater than fine threads. Okay, it's greater than fine threads. So for this coarse bolt, the thread height, okay, is greater than the fine thread. And the coarse thread have the larger volume materials between. Okay, and the coarse thread boasts offer good resistance to thread stripping as compared with the fine thread bolts. Okay, so so this is an example of the stripped thread here. So we can see here. Okay, so when the sorry. Okay. Okay. So when the thread engage is short, okay, that's mean the distance, right? The engagement length is short. Coarse threads are preferable due to their high stripping length. Okay, that's mean the contact, the surface contact, the surface contact between the knots and the screw has the higher area contacting with each other between the thread, the bolt thread, and the nut thread. Okay, and this higher surface contact providing the higher stripping strengths, Okay, so thread Argolin's less likely to occur in coarse pitch bolts as compared with then fine thread, right? That's why I mentioned, because the contact area between the bolt thread and the nut threads are greater than that of the fine thread, right? And because fine threading requires many more turns per inch, which generates more friction. Okay, and the excess friction dramatically increases the change of the galley and fastening. So I already mentioned this before. Okay, and now we can define we can have the two types of the thread. One is the square, and the second is called the Acme thread. Square and Acme thread are used when the threads are intended to transmit power. So we're going to use the thread to transmit power. You have to consider whether you're going to use the square or Acme thread. Okay, and what's the difference? What's the difference? Acme and standard. The difference is the thread angle, right? The thread angle for the Acme thread is 29. It's 29 degrees. Okay, it's 29 degrees. Okay. And this table just presents some preferred pitch for the Acme thread right here. Okay. The pitch and the diameter. The pitch and the major diameter. Okay. Major diameter, root diameter. Okay. Okay, so there's one example of the component by using the square thread or the Acme thread. It's called the power screw. Okay, can be used to change angular motion into linear motion. Right, so for this power screw is rotated, right? And we can just keep rotating this power screw and transmit power. Okay, and transmit power to make this maybe this is a shaft, or we can convey some components linearly in linear motion. Okay, usually transmit power. The examples including the vices, or the presses and jacks and lace screw on lace and so on. Okay, and so on. Okay, so let's focus on the square thread first. Okay, so suppose the thread is in square, and which is com compact or installed with the knots. Okay, it's a notch element, but not just a knot. Okay, we can regard it as the notch element. Okay, and the most screw follow the right hand rule, and knot element can be not equal to the actual units, and the angular motion with respect to the screw is, we can define the angular motion with respect to the screw. Okay, suppose if we follow the right hand rule. So suppose we have the power screw, right? Power screw, and one end is fixed. So when we rotate it, we only rotated this knot element, and it will move down by following the right hand rule. Okay, and if it's a two components, the screw bolt and the knot element are free, and we can rotate it. The screw bolt, right? And this knot element will move down. And if this knot element is fixed right here, is fixed, and the only component can rotate it is the screw bolt. Okay, so in this case, when this screw bolt rotated, and this screw bolt will move up, right? Okay, will move up. So we can define the relative motion of the knot element, okay, based on the power screw, okay, the power screw. Okay, so this is the example here. So we have the square screw here, okay, compact with a knot element, and is for conveyed or is for raising or lower a mass. Okay, suppose this is your load, okay, your something, okay. So we can raise or lower this knot element for lifting this mass, right? Lift this mass. Okay. 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 So suppose we focus on 2 points on this power screw. The 2 point, okay? Point A and point B. Okay. At the same position. Okay. The same position. And the distance between this 2 point A and B is L. Okay, is L. And the lead angle, we can define the slope, okay, right here. Okay, so the slope of the square thread with the horizontal line. Okay, so it's the lead angle. Okay, this is the lead angle. Okay, so if we stretch it, we just expand it. We stretch this point AB into a straight line. Okay, we can just stretch it. For example, just fix one point here, right? So we can just stretch out, extend this part, this screw, this thread, right? So we can just stretch it. Okay, so we can find the triangle like this. Okay, right? We just stretch it, just extend the point A and B, right? And as what I mentioned, the distance between the point A and B, the vertical distance between the A and B is lambda, right? And the angle, right, is the distance between A and B vertically is L, and the angle is lambda, the lead angle, the lead angle. Okay, and the surface of the AB, surface AB is the thread surface. Okay, the thread surface right here. Okay, it's the thread surface. The thread surface. Okay, the thread surface. Okay, so if we look into the force equilibrium on this triangle, or we say on the surface AB, what we get, what we get. Okay, so we have the mass, right? That we're gonna lift it, or we are gonna raise it, this mass, right? So this force, right? The mass from the mass. Of course, there's a normal force perpendicular to the thread surface AB. Okay, the thread surface AB. And there's a friction force. There's a friction force along the surface, the thread surface AB equals to the F, the friction coefficient, time the normal force, right? Okay, and we need the PR. It's the force for racing to reach the force equilibrium sigma Fy equals to 0 and sigma Fx equal to 0. Okay, so from this free body diagram, we can figure out its equilibrium equation, right? Sigma Fy and sigma Fx equals to 0. Okay, so we can solve this equation and this equation, right? It's quite fundamentally. And finally, we got the PR. What is the PR? PR is the force required to lift the mass or the load. Okay, the force required to raise the mass or the load. Okay, and we both divided the denominator and denominator by cosine lambda. Okay, we find this PR, right? And we define this cosine lambda and divided by cosine lambda. And we get the PR equals to, in terms of the force, right? That is the load, okay? The force and the lead angle and the friction coefficient. So the PR is a function of the force, lambda, and the friction coefficient, okay? Okay. So we can say from this triangle, right? We can find the tangent lambda equals to L over pi times the dm. The dm is the mean diameter. The mean diameter. Okay, the mean diameter is right here. Okay. Okay. Okay, the mean diameter. Okay. So therefore we can say if we regard this as the power screw, right? So we need a force PR to lift or to raise the load, right? And there's a torque applied equals to PR times the radius, and radius equals to the mean diameter divided by 2. Okay, divided by 2. Okay, divided by 2. So the force required to raise, right? That's we already figure out from the equilibrium, force equilibrium, right? So the torque, right, equals to the PR times the radius. The PR times the radius. Okay. So the PR, right, times the radius. We got the torque. The torque to raise the load. Okay, the torque raise the load. Okay, so there's a concept I'm gonna clarify that usually we don't much care about the force. Okay, for example, if we're gonna use the wrench, we always have to consider the torque. What's the torque that we that require? Okay, to raise or lower, to fasten or to fix, okay, the knots, the components, whatever, right? Because the force is not easy to define. However, the torque is what we have to be defined. The torque has to be defined, okay? Therefore, the torque, right, equal to the PR times the radius, okay? The radius. Okay, so we can just rewrite this equation, right, in terms of the torque, right here. So we find the torque to raise the load will equals to this. Okay. Okay. So the TL is the lower, the TR is the raise. Okay, so the same thing if we're gonna lower the load, right? What's the torque that we need is defined as the TL. Okay, the TL. The same process we can obtain by this force equilibrium, right? So basically we just need the force, the PL, to lower the load. Okay, just repeat this force equilibrium equation to figure out the force and the torque to lower the load. Okay, so if the pi FDM, pi FDM right here is less than L. L as the distance between the point A and B, right? Vertically. Okay. If the pi FDM is less than and equal to the L, the TL will be less than and equal to 0. That means no torque need to lower the load. So what's this mean? What's mean the no torque needed to lower the load? What's that mean? That means even we have the nut components, okay, with the screw thread, right? So when we just release the nut, and this nut will move down automatically, freely, because the TL is less than and equal to 0. Okay. And if this pi FDM is greater than L, that means the TL is greater than 0. So in this case, the knot is self-blocking. Self-block it. So that means when you just let it go, let this knot element free without any force applied to it, without any torque applied to it. Okay. And this knot element will remain at that position. And it will move down. Just keep there, stay there. Okay, just stay there. Okay. Okay, so this is what I mentioned previously. This is the M, the main diameter. Okay, so we can just define that the properly is right here, and right here is the main diameter. Okay, okay, and the lambda. Okay, and the pitch. Okay, okay, and the knot. Okay, so the first we just figure out this PR, right? The force required to raise the load. Okay, in opposites, we can define the PL. Okay, that is the force required to lower the load. Okay, the lower the load. Okay. Okay, so this shows force equilibrium again. Okay, so just remember that. I'm gonna skip this. So we can find the PR and the PL, right? PR and PL. Okay, so if we divided the numerator and denominator by cosine lambda, right? And using the relation, the temperature lambda equals to L over pi dN, right? Applying plug in the above equations, and we can get this PR and PL in terms of the force L and dN and the friction, okay, the friction. Okay, so noting that the torque is the product of the force and the mean diameter, right? So we got the final two equations. That is the TR, the torque needed to raise the mass, to raise the load, right? Or the TL, the torque need to lower the mass. Okay, raise and lower. Okay, raise and lower. Okay. Okay, so in general case, we have to take into account the collar friction. That's mean for this power screw or the screw thread, one end must be fixed in a non-rotating stage. And this screw or screw must have the collar contact with this non-rotating stage. And in this interface, the friction must be there, right? The friction must be there. Okay, the friction must be there. Okay, so if we look into this interface between the collar and the non-rotating stage, right here, right? So this yellow region defines the contact area between the collar and the non-rotating stage. Okay, non-rotating stage. So there's a point load. Suppose we have the point load, the node perpendicular to the face, the surface, right? Which equals to the normal force N applied to the surface, right? And this N times the friction coefficient between the interface of the collar and the non-rotating stage, we get the friction force, Okay. Okay. So the R is defined as the collar radius. That is the diameter of the collar divided by 2, right? And therefore the friction equals to F times N. F is the friction coefficient, right? Equals to F times the F, the point load. Therefore the TC, C here represents the collar here, okay? Equals to the friction times the radius. Okay, therefore the TC equals to F times FC. FC represents the collar friction. Okay, times the DC over 2. That's the radius. That's the radius. Okay, therefore the torque generated from the friction between the collar and the non-rotating stage defined as the TC. The TC. Okay, it's the friction collar torque. Okay, between this interface. Okay, between the interface. Okay. Okay. So that's okay. So that's just recap what we already learned for this TL. So if the loading torque, the TL, okay. So the loading torque defines the TL. Okay, it's TL. It's negative. The load will lower itself by causing the screw to spin without any external effort. Okay, lead is large or friction is low. So what's the situation to make the loading torque is negative? That's mean the lead is large. Lead, what is the lead? It's the distance, right, between the point A and B, right? Remember that. And or the friction is low. Okay, the friction, the surface, the screw surface contact with the nut element and the friction between them is low. That's mean the TL might be negative. Okay. If the loading torque, if the TL is positive, greater than 0, the screw is self-locking, right? Self-locking, that's me. I just let it go. That did not go. I just release the nut element, and it will stay there. It will stay there. Okay, it will stay there. Therefore, the self-locking condition is defines the pi f dm greater than L. Noting that the L over pi dm equals to tangent lambda. The self-locking condition can be seen to only involve the coefficient of the friction and the lead angle. Okay, so when this condition match, that's mean the self-locking condition occur. Okay. Okay. So if the screw thread is very steep, okay, that is if it is a high lead angle lambda, the friction force may not be able to overcome the tendency for load to slide down the plane, and the load will fall due to gravity. In most cases, for power screws with single threads, however, the lead angle is rather small, and the friction force is large enough to oppose the opposite the load and keep it from sliding down the plane. Okay, such as a screw is called self-locking and a desirable characteristic for jacks and similar devices. Okay. Okay, so what's the efficiency of the power screw? The power screw. The torque. needed to raise the load with no friction, losses can be found. So the torque needed to raise the load without friction loss. Okay, that's mean the friction coefficient equals to 0. Oh, that's mean we get the 100% efficiency of the torque, right? The T naught equals to FL. The F equals to 0, right? So the torque needed to raise, that's mean the TR, right? Okay, so if we look into this TR, right? So this F equals to 0, this equal to 0, 0, and equals to 0, right? Only for the TR, which is 0, 0, right? Okay. Oh, sorry, I forget. One thing is that okay. So let's go back to here. If we figure out this TC, the friction column torque, we can combine this TC with this TR and TL. Okay, what we already write out from the previously, right? So this T race, we can combine, we can integrate it with the FC and RC. Okay, FC and RC. Okay, so this is the torque required to raise the load W or F. Okay, so this TR is already integrated with the TC. And the same thing, this TL is integrated with TC. Okay, integrated with TC. Okay, so if we define the friction coefficient equals to 0, we got a T naught equals to FL, F times the lead divided by 2 pi. And the efficiency of the power screw is therefore E equal to the T naught divided by TR. Okay. The T naught means the no friction. Okay, no friction. And the TR means the load to raise the load. Okay. We can figure out what the efficiency is of the power screw. Okay. Okay, so now let's look into this the power screw with active thread. Okay, so this is one question. For the square thread and the active thread, both of them can be using the power screw, right? Can be using the transmitting power. Okay, so which one has the higher uh, torque, has the higher efficiency? Is it active thread or the square thread? Which thread has the higher, we can say the higher power to transmit it? Right? Because from, of course, geometrically, we can figure out the square thread should have this higher efficiency to transmit, transmit power, right? To transmit has the higher powers. Why? Because the force for this square thread, let's go back to look into the, let me see where, okay. 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 So we can look into for this square thread, right? And the force is applied to perpendicular to the surface, the thread surface. However, for the active thread, the force applied to the thread surface with a specific angle, right? With the thread, half of the thread angle. So that's mean the force is gonna be separated, right? So it's gonna be partial of the force applied to the Acme thread surface. Therefore, for this power transmission point of view, the square thread can provide a higher power or the high efficiency to transmit some product or mass or load. Okay. Okay, so if the Acme thread are used instead of the square thread, the thread angle creates a wedging action. Okay, wedge action, and the friction components are increased. Right? The friction components are increased. Okay, and the torque necessary to raise the load or tighten the screw is found by dividing the angle, the alpha friction terms, okay, of the equation A.1 right here. Here. Divided this equation by cosine alpha. Cosine alpha, alpha is the half of the Acme thread angle, right? Okay. So that equation divided by the cosine alpha, we get this torque needed to raise the mass by using the Acme thread. The Acme thread. Okay. So if the lead angle can be neglict. Okay, if the thread angle can be neglict when the alpha equal to 0, that means the thread is the square thread. Okay, the square thread. Okay, it's the square thread. That means the second alpha equals to 1. Right? The second alpha equals to 1 and 1. Right? So it's the same as the torque required to raise the mass or the load in the square thread, right? Okay, so for the screw that have a thread angle rather than 0, so we can define define this two torque, right? The torque need to raise the mass, or the torque required to lower the mass. That means the alpha is not equal to 0. The alpha is not equal to 0. Okay. Okay, so any questions? Okay, so there's one example. Maybe I just skip it. Okay, so I'm gonna stop here. Next time I'm gonna deeply introduce the stresses apply to the power screw. Okay, so what's the stresses analysis? What type of the stresses apply to the power screw and knots? Okay, so that will be the next subject that we are gonna focus on. Okay, so maybe we're gonna stop here.